terms of the number of reverse pairs. That's tedious. Let's do it the quick way and just do it by counting the number of cross points or intersections between the lines when you connect 1 to 1, 2 to 2, 3 to 3, blah, 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 blah. Right? Now, so we're swapping R and S because it's a transposition that swaps R and S. These R and S, they're just the labels, if you like, the numerical IDs of the objects that you're permuting. So this is object R gets swapped for object S, and object S gets swapped for object R. Right? Now, you can actually calculate the number of cross points, but well, that was Barnard's way. But I'm more a physicist, and I like thinking in terms of symmetries. So I don't really care about what this actual number is. All I care about is there's a kind of symmetry here, right? How many points you have here, cross points you have here on the right-hand side. There'll be equal number on the left-hand side, right? If you're like a mirror symmetry about this central point where the two lines cross. So, right, by symmetry. So whatever this number is that does not include this center point here, whatever that number is, just double it by symmetry, and then you've got this center point here which gives you a +1. So whatever this number is, it'll be doubled, so that's an even number, right? +1, the middle point here, +1. So that makes it an odd number of cross points, an odd number of, what's the word? Interconnections? Intersections? Yeah, whatever. Yeah, I prefer cross point. So, okay. Alright, so the number of cross points is odd. Now if the number of cross points is odd, the number of reverse pairs is odd because we did a theorem showing those two are the same number, right? For each reversal you get one cross point. One cross point, one reversal. It's sort of 1 to 1, right? So we prove the number of cross points is odd, and therefore the number of reverse pairs is odd, and therefore this transposition is odd. Okay? So we proved it. So a transposition is an odd permutation. Remember that? Transposition is an odd permutation, and we're going to use that later. Gets quite powerful. How do I put this? I think I've mentioned it before, but a lot of pure mathematicians talk about the beauty and the power of pure mathematics, and I think towards the end of this session, especially when we get around here, I hope you get that feeling as well, because we're starting to have quite a few tools under our belt, and with those tools we can do some powerful stuff, right? And but believe me, this is just the beginning. We get up to sort of PhD level in this stuff, and you're building like cathedrals of mathematical logic. Incredibly beautiful, powerful stuff, and highly relevant to the physical world. I mean, the physicists, the mathematical physicists, the mathicists, you know, the guys who are just as much at home in pure mathematics as they are in mathematical physics. And for them, it's sort of merged. So I sort of see myself as a mathicist, right? I do math and physics merged. All right. Okay. All right. So next theorem, which will actually use this one, quite a powerful result. So if you have a permutation that's even, it will have an even number of transpositions. Remember every. It's from the previous session. Every permutation can be expressed as a product of transpositions, right? Product of transposition, and these cycles of length 2. Okay. Now, if that permutation, I just call it perm here for short, if that permutation is even, the number of transpositions it will have will also be even. And if that permutation is odd, if the permutation, and if An odd permutation has an odd number of transpositions. Right? That's a theorem statement. Now, how to prove it? Well, we use theorem 41 from previous sessions. Now, I've written it down again here to remind you, and it's quite a powerful theorem. And now we'll start using it. We'll use it several times, and you'll begin to appreciate its power and its usefulness. Okay. Now, can you remember? Well, here's the statement, the theorem statement of theorem 41. So remember what this big N means. It's the number of reversed pairs of this permutation. Now here this reading from the right, this xy, or reading from the left, yx, that's the permutation you get by first doing permutation x followed by permutation y. So this n, big N here, this term here, is the number of reverse pairs after you transform x and then y. Okay, and that is equal, now n of x, that's just the number of reverse pairs, or cross points, same thing. Cross points, same thing. Remember, that's a different theorem. The number of reverse pairs is equal to the number of cross points. Okay, so this is just the number of reverse pairs or cross points after you do permutation x, and this is the number of reverse pairs or cross points after you do permutation y. Okay, and you just add them. Right? Now let's see. So if this x, now the x and y, they are just permutations, right? And a transposition is just a special case of a permutation, but still a permutation, right? So T here stands for a transposition, so a cycle of length 2, right? Now, the number, well, a transposition is odd, right? We proved that here. That was in theorem 44. So if it's odd, by definition, it has an odd number of reversed pairs. It has an odd number of cross points. Okay. Now n here, this is the number of reverse pairs. That's what this n stands for, or cross points. Now we showed just before a transposition has, well, a transposition is odd. It's an odd permutation, right? So this number here will be an odd number, right? Because it has an odd number of cross points. This t. Okay, so this is an odd number. So minus 1 raised to an odd number gives you -1. Okay, so remember this. We'll use that. Okay. Right. Now, x here is just an arbitrary permutation from your what's the word? Symmetric. Getting a little tired, I guess. Symmetric group, right, of n objects, and you know you can write your any permutation as a product of transpositions, right? These cycles of length 2, right? So let's take that's a general form. Now we don't know how many transpositions you need. So let's just say it's k, integer k, right? So transposition 1, and then you do transposition 2, ... transposition k, t or t of k, tk, right? So that's the general form. All right. Now let's take theorem 41, this statement, and generalize it. So instead of having just the product of two permutations. Let's have k of them. Right? Now these are just, okay, they're transpositions, but transpositions are permutations. So if you put an x here, if you put this x here, you can generalize this. This is just with two representations, and it splits into a sum of x and y. So generalize it now, and so x now has k, the product of k permutations, right? So you plug this into here, and you'll get n of t. N of tk plus n of tk minus 1 plus dot 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 plus n of t2 plus n of t1. Right? So you just plug this into here. And instead of having two terms, you've now got k terms. So you'll have k terms here in the sum. Right? That's just a generalization of theorem 41. Okay? So here, this is like, you sum all these, and the whole thing, the sum is a power of minus 1. So this line here, this is a generalization of this statement. All right? Okay. So these are just exponents. So you can rewrite this as this. So it's just minus 1 to that times minus 1 to that times minus 1, and so on. So you get this sort of expression, right? And you get this kind of thing, k times. I hope you're following all the details. It gets quite detailed, right? Now, what is this? These k's here, you know, tk minus 1, t2, t1, they're all transpositions, right? And minus 1 to the power of n of a transposition is of this form, okay? This t here is just a transposition. That's a transposition. Minus 1 to the power n of a transposition is minus 1. We just proved that, right? All right. So this is of that form. So it's minus 1. So this is minus 1, and that's minus 1. Same logic. So you got k times. You got minus the 1 to the k. All right. Here's minus 1. That's minus 1. That's minus 1, and you've got that k times. So you multiply all these k times, and you get minus 1 to the power k. All right. Okie dokie. So in other words, this is equal to that. And what does that imply? Now, what is k? This little k. I mean, think about it. What is its meaning? What is k? It's here. K is the number of transpositions, right? You form this product of